Hello everyone, I am Sandra and I will be presenting our work entitled The Background Also Matters, Background-Aware Motion-Guided Object Discovery. Motion-guided object discovery focuses on using motion dynamics as a means of performing unsupervised object localization. In this task, an object is defined as any entity that is capable of moving. The motion guidance signal takes the form of binary masks of moving objects, which are derived from the optical flow by mapping it to the masks of object instances. This mapping is learned using synthetic data, then applied for inference only on real-world scenarios. The predicted masks of moving objects are incorporated into the MGOD framework to direct the model's attention towards all similar objects, both moving and static. However, since MGOD methods typically rely on a slot attention architecture, where the slots are designed to compete for explaining different parts of the scene, MGOD methods encounter an issue of over-segmentation in non-object regions. This is particularly problematic given the unsupervised setting, where object segments are indistinguishable from noise segments resulting from over-segmentation. It is important to note that this issue is not directly related to the quality of the guidance signal, as it persists even when using ground truth masks of moving objects, which is not a desired behavior for a segmentation model. In this work, we address the previous issue by introducing BMOD, a simple yet effective learning mechanism that can be incorporated within MGOD approaches to enable background modeling. In the following, we detail the components of the proposed method. The video sequence encoding employs a similar process as in MGOD approaches to obtain a spatiotemporal representation for each frame. The slot attention mechanism operates on this representation to split it across k embedding vectors named slots. The associated attention maps indicate the regions captured by each slot. Among these, we designate a specific slot for the background class, and we wanted to capture all non-object regions. Given the lack of information on the background pixel's positions, we opt for an indirect modeling of the background through the learning of its complementary class, which is the foreground. With foreground, we mean all objects, both moving and static. We formulate the problem as one-class learning, which is a common approach in binary classification. In our case, the positive class corresponds to pixels of moving objects, and our goal is to distinguish static objects from the background in the remaining regions. For this purpose, we use all available motion masks whose sum represents the moving foreground. Our aim is to extend it to the true foreground composed of both static and moving objects. We propose learning the true foreground using regularized negative log likelihood loss. The negative log likelihood encourages the extension from moving to static objects, while regularization prevents activating all pixels within the foreground map. Once the foreground is learned, the background is consequently allocated to its dedicated slot, preventing noise from emerging in other object slots. The attention of object slots is directed by each motion mask individually, following the core principle of MGOD. However, introducing the background class in our method, which is the predominant segment in a scene, introduces the risk of small objects being associated with this class and so non-detected. To prevent this, we use a weighted binary cross-entropy, where the weight is inversely proportional to the object size, emphasizing smaller objects. Similar to previous MGOD approaches, the sum of all slots, weighted each by its respective attention map, is passed to the decoder to reconstruct the input frame using the mean-squared error loss. The overall loss used during training is the sum of all previous objective functions. To validate BMOD, we conducted two separate tests. First, we evaluated the foreground object segmentation following the evaluation protocol commonly used in object discovery. This test was conducted using the parallel domain dataset, which consists of photorealistic road scenes, and the real-world dataset Kitty. The obtained results show that background handling enhances the localization of foreground objects, even though the proposed method isn't primarily aimed at this task. In the second test, we evaluate the background-aware object discovery task. We introduce the computation of all ARI metric by incorporating the background cluster into the evaluation. The achieved results provide a strong baseline for background modeling in the unsupervised setting and show the capacity of BMOD to scale in the supervised setting. Several ablative studies helped to further understand the components of the method. In particular, we infer the importance of the weighting by object size in BMOD, as well as its ability to scale with an enhanced quality of pseudolabels. We present qualitative results illustrating background handling on parallel domain and KT datasets under the two studied settings using estimated pseudolabels in the first and ground truth motion supervision in the second. The essential takeaway from BMOD is that it is a simple yet effective learning mechanism for background modeling in motion-guided object discovery. We showed that the proposed background handling not only reduces the noise in non-object regions, but also enhances the localization of foreground objects. The approach also demonstrates efficient scalability with enhanced quality of pseudolabels. However, the gap between the supervised and unsupervised settings is still large, suggesting the advantages of enhancing the quality of pseudolabels. Achieving such enhancement is possible, for example, by incorporating MGOD within a pseudo-labeling loop, facilitated by the noise reduction provided by BMOD. This is a promising avenue for future work. Thank you for your attention.